Okay, this is going to be one of those lectures that involves a little bit more mathematical formalism than usual. The reason that I've chosen to go over some of this, I normally don't do a lot of this in this class, but this particular case, a lot of the definitions that we'll make have pretty far-reaching implications into a lot of areas in electrical engineering. So it's worth spending a little time to discuss a little bit of theory, make a few formal definitions, and go over some theorems. I actually break this lecture into two parts, so this will comprise part one. So a lot of these concepts we've talked about in a previous lecture. I want to put a little more formalism in with it today in this lecture. Let's review first of all what elementary row operations are. If you remember, there are three. We can interchange two rows. We can have the addition of a constant multiple of one row to another row, or we can multiply a row by a non-zero constant c. And so what happens is, after we've done these row operations, however many of them we wish, we now have some linear system S2 that resulted from a number of row operations that we formed from an original linear system S1, and we refer to those as being row equivalent. So theorem number one is that row equivalent linear systems will have the same set of solutions. So for this reason, we're able to do Gaussian elimination, and that then allows us to solve an easier system of equations that we've obtained through row operations. Also talking a little bit about what happens when we have a different number of equations than unknowns. So if we have a system of equations that has more equations than we have unknowns, that linear system is referred to as overdetermined. If our number of equations is equal to our number of unknowns, then that situation is called determined. And if our number of equations is fewer than our number of unknowns, we refer to that as undetermined. Another definition is consistent versus inconsistent. So a system is called consistent if it has at least one solution, but it's called inconsistent if it has no solutions. So if you look at this example, clearly we have x1 plus x2 equal to two completely different things. There's no way both of those statements can be true, so that would be an example of an inconsistent system. Graphically, you can probably also visualize what this would look like, that one of these equations, basically this would form two parallel lines. So if you think back to our previous lecture where we gave some physical examples or some picture examples, this would be an example of two parallel lines that never have an intersection, so we actually don't have a solution. We can visualize that because this is in two dimensions. Now, row echelon form, if you remember, as we do our Gaussian elimination, the goal is to get a series of rows where we have the first non-zero element in the row, and then in the second row we would have the first element being 0 and the second element being non-zero, and so on. We've basically gone through and done a Gaussian elimination, and this is on either a square matrix or an augmented matrix. And once we complete this process, this is referred to as row echelon form. And so you would have your non-zero coefficients forming an upper triangle and zero coefficients in the lower triangle, excluding the diagonal. So in row echelon form, if you have rows of zeros, you'll always find them in the last rows or the bottom row. And so for every non-zero row, the leftmost non-zero entry is farther to the right than the previous row. So that's just kind of a fancy way of saying it forms an upper triangular matrix. So for instance, in this example, the coefficient matrix and its augmented form are shown in row echelon form. So what can we determine from row echelon form? Well, if we have some original system of m equations and n unknowns, and it has an augmented matrix where A is our coefficient matrix and B is our solution column, this can be row reduced to some matrix that has rows R or a row echelon reduced form R and right-hand column F. So these two systems, AX equal B and RX equal F, are equivalent. So if one of them has a solution, the other one also has a solution, and those solutions will be identical. So after we do Gaussian elimination, we have something that looks like this, where we have row echelon form of an augmented matrix, and then these blue triangles would represent where we would have zeros. So this is an example where we had some matrix A. We did a lot of row operations so that we could reduce it to some matrix R. And so the next definition that we want to make is the definition of the rank of the matrix. So essentially, after you've done Gaussian elimination and you have your matrix in row echelon form, the number of non-zero rows, so in this case that would be little r rows. Sorry about the double R notation, that's a little confusion. So the number of non-zero rows is called the rank of the matrix. So this matrix would have rank R. Now the rank of the matrix in row echelon form is the same as the rank of the original matrix A. So just because an original matrix appears to have a lot of rows and columns, it's not until we reduce it to row echelon form to get our reduced coefficient matrix that we can actually determine the rank. So here's the method for determining whether some system of equations AX plus B has solutions and what they are. It's not going to have a solution if R is less than M, which means when you reduce this to row echelon form, that your matrix R will have at least one row of all zeros, and at least one of the numbers, in other words, at least one of those column numbers on the right is not zero. Then the system Rx equal F is inconsistent and we don't have a solution. So that would mean AX equal B is inconsistent as well and also does not have a solution. Now if the system is consistent, so either the number of rows is equal to the number of variables or the number of rows is less than the number of variables, and all of your numbers F, R plus 1 and so on, so that would be the numbers in the bottom. So this is R plus 1. So this is below the triangle where you have non-zero rows. Then there are solutions. You have a unique solution if the system is consistent and R is equal to N. Then there's exactly one solution, and that can be found by back substitution. If you have infinitely many solutions, then basically what happens is for every value of x greater than R, you arbitrarily choose a value. And then you solve the rth equation for x sub r and go back substitution to solve the previous equations. So let's go back over that. This would mean, for example, and let's go back, this would mean that in these rows, for these variables, you're going to have to select a value. So you're going to have to select a value for your variable from the rank R up to the number of equations M, because they're not solvable from a matrix method. So this is called a parameterization approach. In other words, and this can be actually a physical problem. You might have some situation where you have a set of equations and there's a variable that you don't really have a solution for, so you may pick a number for that variable and find the solution for that number. You may pick another number for that variable and find the solution for that number. So let's say you're trying to predict various things based on temperature patterns, and you don't know the next day's temperature. So what you can do is you can set various temperature ranges or various temperature values, parameterizing the system, and get a solution for each one of those variables. And there are an infinite number of variables or an infinite number of solutions that you could choose for that variable that's non-specified. So that's why it's referred to as a parameterization approach. A lot of times in the real world, there's a limited realistic range that a variable can exhibit. So for example, if we were talking temperature on planet Earth, obviously there's a limited range of values. So you would be able to parameterize that over whatever range of variables was reasonable. So that would be a case where we would have infinitely many solutions in the mathematically abstract world, but maybe some limit on realistic solutions in the physical world. All right, well, let's talk a little bit about linear independence and dependence of vectors. So what does it mean when vectors are linearly independent? So really, the way we prove this is to show what linear dependence means. So let's suppose we have some set of vectors, and let's let there be m of them. So we can make a linear combination of those m vectors, and we will have these constants or scalars, c1 through cm, and they can be any scalar. And so now let's consider an equation where we would have these coefficients times these vectors equal to 0. So there are a couple of obvious ways this can happen. One way that can happen is we let every value of scalar equal to 0. Then obviously 0 times anything is equal to 0, so it'll be 0 equals 0. Now if that's the only case where you can get 0 by summing a linear combination of these vectors, then we say these vectors are linearly independent, or they form a linearly independent set. If on the other hand there's some other set of coefficients that we could choose where they are not all 0, so maybe all but 2 of them are 0, but if we choose those 2 to be a certain value, we end up with a 0 solution, then we do not have a linearly independent set of vectors. So what this is really saying is that if you have one vector and you can multiply it by a constant and add it to another vector and get 0, those 2 vectors are not linearly independent because one would actually be a multiple of the other. So this just repeats what I just said, that if this holds when all scalars are not 0, these vectors are linearly dependent. We can express at least one of the vectors as a linear combination of the others. So how does rank of a matrix and linear independence relate? So remember, the rank of a matrix A is the maximum number of linearly independent row vectors of A, and that's denoted by rank A. So we call a matrix A row equivalent, A1 row equivalent to a matrix A2 if A1 can be obtained from A2 by some finite number of row operations. And the maximum number of linearly independent row vectors of a matrix does not change. So if we change the order of rows or multiply row by a non-zero constant or take a linear combination, the rank is invariant. So it's invariant under elementary row operations. So the rank is going to be a constant for a given set of linear equations. So by reducing a matrix to row echelon form, not only can we determine the rank, we can also determine how many linearly independent vectors we have. So this leads us to Theorem 1, which essentially states that row equivalent matrices have the same rank. Now, how would you determine a rank? You basically determine a rank by putting a matrix in row echelon form. So this is an example. We've had examples of how to do this before. This is Gaussian reduction. Notice that we basically are not going to change row 1. Why is that? Because it's allowed to have a constant as the first element in row 1. So we're going to start by trying to get rid of this first constant in row 2, and then we'll try to get rid of the first constant in row 3 as well. So these operations will allow us to do that. Continuing on the next page, the next thing to do is to try to get rid of this constant in row 3. But notice when we do that, suddenly the entire row goes to 0. So essentially this says that this matrix had a rank of 2 and only had 2 linearly independent variables. Theorem number 2, linear independence and dependence of vectors. We're going to consider p vectors that each have n components. These vectors are linearly independent if the matrix formed with these vectors as row vectors has a rank of p. But they're linearly dependent if the matrix has a rank of less than p. Theorem 3 says that the rank of a matrix A equals the maximum number of linearly independent column vectors of A. And because of that, A and its transpose are going to have the same rank. Theorem 4 tells us to consider p vectors each having n components. If n is less than p, then these vectors are linearly independent. So a vector space, the maximum number of linearly independent vectors in some vector space, is referred to as the dimension of V. A linearly independent set in V consisting of the maximum possible number of vectors in V is called a basis for V. And we're going to see this word basis or basis set appearing a lot. So in other words, the largest possible set of independent vectors in V forms a basis for V. So if we add one more vector to that set's going to be linearly dependent. So the number of vectors of a basis for V is equal to the dimension of V. Now the set of all linear combinations of a given vector with the same number of components is called the span of vectors. So a span is a vector space. And so if in addition to these given vectors that are linearly independent, if they are linearly independent, they form a basis for the vector set. So basically, a set of vectors is a vector space if, first of all, the vectors in the set are linearly independent, and secondly, any vector in V can be expressed as a linear combination of the vectors in the set. So the set of vectors spans the vector space V. Okay, finally, Theorem 5 says that the vector space R sub n, and this is just a way we denote a vector space, consisting of all the vectors that have n components, n is a real number, has dimension n. So we often talk about n-dimensional space. And then finally, Theorem 6, the row space and the column space of a matrix A have the same dimension, and that dimension is equal to rank A. Okay. Finally, if we have some given matrix A and we have a homogeneous system A times X is equal to 0, that's a vector space and we refer to it as the null space of A. And the dimension of the null space is referred to as the nullity of A. So if we take the rank of A and we add the nullity of A, we basically have the number of columns that are in A. We'll continue with some additional theorems and discussion in the next part of the lecture. As I said, I'm breaking this lecture into two parts because there is quite a bit of material here. So we'll end this particular portion of the video here.